Okay, so we'll go ahead and get started. My name is Travis Brown. I want to thank John for inviting me here to talk about the CERC project and specifically about the generic type class instance derivation that we have in CERC, which is it's one of the parts of the library that I'm most excited about. Before we get started, how many people here have heard of CERC? Okay, that's heartening. How many people have used CERC? Okay, so it looks like about a quarter of the room, a third of the room. How many people have specifically used the generic derivation in CERC? Okay, and how many people have used CERC but not? Okay, and then I guess lastly, how many people have used generic derivation in other Scala libraries, whether it's scodec or? Okay, great. So this won't be new to most people. All right. So just to start with the high-level goal for this talk, I wanted to. These are paraphrases of some of the feedback that I've gotten from adopters of CERC over the past year, and I want to address some of these complaints or concerns, and more generally demystify this technology that we have in Scala now. The opportunities for generically deriving our type class instances. So some of the things we'll talk about are ways that we can make this feel less magical, ways that we can make it more predictable, more comfortable, where it doesn't feel like it's just something that you're dropping into your code and that it's doing a lot of work that you don't necessarily understand. Also, we'll look at just briefly at some of the issues in the compiler that do cause problems for generic derivation. I'll talk, the second half of the talk especially, we'll look at some of the techniques that CERC has used to improve compilation times, because that's one of the things, especially in the earlier releases, a lot of adopters found it just completely prohibitive especially for very large ADTs or deeply nested case class hierarchies. And then lastly, the thing that I'll wrap up with is a kind of preview of some configurable generic derivation features that are coming to the next version of CERC. Hopefully very soon, in the next week to month. Okay, so at a high level, we're going to talk about, I'll spend just a little bit of time talking about what this is, what it does, but I don't want to spend a lot of time on just the definitions. And then how we make it predictable and robust. So there are implementations of type class instance derivation out there for various libraries that they're very useful for some cases, but then they will just suddenly not work when you try to derive an instance for a generic case class, or you try to derive an instance for a ADT, a sealed trade hierarchy, instead of a case class. So we'll look at ways that we can make this something that when you apply it, it will work in the cases that you expect it to work, instead of having these gaps that it doesn't cover. And then we also want this to be something that is intelligible, that is implemented in a way that is easy to reason about and to maintain. And then, so Martin was mentioning this morning that in some cases when you have very implicit, heavy code, you can get compile times of 1 line per second. And honestly, some of the stuff we'll be looking at here, it's more like a third of a line per second. That this can, if you are not being careful, really slow down the compiler dramatically. And then lastly, the configuration. So those are the high-level issues and questions that we'll be looking at. But also, I just want this. So one of the things that, as I've been working on CERC and other libraries, there's just so much lore around this, around the concept of generic derivation. So there are implementations in probably I don't know, a dozen, 20 different Scala libraries of one kind or another, but often there's just not a single good place to go for information about the techniques that are used in the different libraries. So we'll do a kind of overview of a lot of these things that if you just stepped into so you'd looked at generic derivation in scodec, which is it can be very clean for reasons that Cersei doesn't have access to. But then you step into the Cersei generic code base, and you just see it looks like a much more complex implementation. So we'll talk about some of the reasons for that complexity. Okay. All right, and so these are some of the things that I'm assuming everybody here is comfortable with the fundamentals of Scala syntax. If it'll be useful, we'll be talking about this idea of algebraic data types, where we build up models for our data using these product types, the case classes on the one hand, and then sealed traits on the other hand. I'll also assume that we'll talk about some specific type classes and what they do, but I'll assume that everybody has some exposure to type classes. The next two are just more useful, but we will go over most of the stuff you'll need to know for today. So we'll talk a lot about shapelist, hlist, and coproduct types, which we'll be using as the generic representation of our ADTs, and then we'll be talking about the role that macros play here, but we won't really be looking at any macro code in much detail. All right, these are some resources that are very useful. So I'm imagining this talk as a kind of follow-up to Sam's Shapeless for Mortals workshop that he gave last December at Scala Exchange. And there are a few other talks and blog posts here that contain material that we're going to review a little bit at the beginning of the talk, but most of the talk will get into the more unpleasant sides of what it takes to implement this stuff in Scala. Okay. We're going to be focusing on these two type classes in Cersei. So I won't spend a lot of time introducing Cersei. It's a fork of the Argonaut JSON library that I started last August. And there were a couple of motivations that I had for the fork. So on the one hand, the CATS project was just getting to the point where it was possible to use it for a library like this, and I was really excited about, or I am really excited about a lot of the direction that CATS is headed. And then on the other hand, I wanted to have a JSON library where I could, where the generic derivation was more tightly integrated with the core library, where if I needed to add pieces, add hooks into the core library to support generic derivation, that would be a possibility. And there were a number of other motivations for the fork, but those were the two primary ones. So the two type classes that we'll be looking at over and over and over are encoder and decoder, where these are just mappings from our Scala types into our representation of JSON values. Okay. Just a quick side note. So encoder and decoder are type classes that characterize types of kind star. So we can have an encoder instance for int, and that tells us how to take an int and turn it into a JSON value. We can have an encoder instance for a more complex type, but still a type that doesn't have any open type parameters, like this map of longs to lists of users. If we know how to encode users, then we know how to encode this more complex type. But these are all types of kind star. So it's also possible to use these methods to derive instances of types that are of, or type classes that characterize types of higher kinds. So there's a project called Kittens, which Miles has been working on, that provides this kind of generic derivation for these type classes that characterize types of kinds star to star, like option, list, these type constructors that we use all the time. Okay. So this talk will focus exclusively on the former, but a lot of the techniques are the same. Okay, so I put together a small library with a few examples, implementations of generic derivation in it. So if you're interested in following along or looking at the material that we'll be talking about in more detail afterwards, this is a repository that contains side-by-side 4 implementations of generic derivation for these Cersei type classes. So there's one that is, it's a pretty straightforward fork from Argonaut's generic derivation, or it's arguably not even generic, but the kind of type class derivation that Argonaut provides in the core library to Circe. And then we've got one that's just a very straightforward, the simplest possible, or close to the simplest possible, shapeless implementation. And then one that uses this really neat idea, the type class, and shapeless, that it's beautiful, but it doesn't really work in the cases that, for a lot of the cases we need. And then we'll look at, so the fourth point here, the last one of the projects in this repository, it's basically what we had in Circe at the 0.3 release. So this is no new macros. It's entirely based on shapeless, but it handles a lot of the corner cases and a lot of the prioritization issues that you run into with the more straightforward shapeless implementation. And we'll be comparing these to the current Circe generic. Okay, so we should get going. All right. So I'll go pretty quickly through this. We've got a case class. We've got some JSON that we want to be able to, we've got a JSON format like this. We want to be able to take documents like this to turn them into our type class if the schema matches what we expect for the type class. And then take our type class and turn it into JSON values like this. And that's not too hard with just Circe core, that it's only a handful of lines of code. It's really clear what's going on if you've worked with Circe. We're just defining an encoder that takes a user, and then we're passing this encoder instance method a function from users to JSON values. So it's straightforward, but if you have 150 case classes that might be nested, that might be parts of these sealed families, these sealed trait hierarchies, this can be a lot of code. And the thing is that this is, in this case, this is entirely mechanical code. That if we look at the structure of the case class, it has three fields. Each of the fields has a name and a type, and we're just basically taking, finding encoders for each of those types and encoding the member value and then putting it into a JSON object with the key being the name of the member. So it's something that we can imagine abstracting over very, very easily. And that's entirely what generic derivation does. So we want to avoid this. We don't want to have potentially hundreds or thousands of lines of this boilerplate in our code base. And so generic derivation is an attempt to make that avoiding that possible. So this is what the same, so here we have the same definition of a case class, and we have a couple of imports, and now we can, because we've imported the contents of this IOCirce generic auto package, we automatically get conversions from any case class where the members have instances of encoder or decoder to an encoder or decoder for that type. So we didn't have to do any of this noisy, simple but mechanical manual implementation. Okay. So all of this is happening at compile time. So the Circe generic it's inspecting the structure of the type, the names of the members, the types of the members. It's finding those encoder instances, creating an instance for the case class, and we're done. And this works for case classes. It works for algebraic data types, and it works for, we can provide instances of shapeless labeled generic for other case classes, and Circe generic will just work with the instance that we provide for those other types. All right. So quick historical note. So we're calling this generic or background information. We're calling this generic because we're abstracting over case classes and sealed families. So Scala provides these tools for building ADTs, but it doesn't really give us mechanisms. It doesn't directly give us mechanisms for abstracting over these structures. And so the standard library doesn't provide this, but this generic and labeled generic, these type classes in Shapeless do provide them. And this is a kind of tongue-in-cheek definition of what generic programming is, but in this case, it actually does apply directly. That these are kinds of polymorphism that our language doesn't support yet. So I guess that means at some point we might have to rename it, but for now, generic works. Okay, one more quick side note. The many libraries would avoid this kind of boilerplate through runtime reflection. So a handful of the popular Scala JSON libraries, and pretty much any serialization library in Scala where you don't have type classes or these richer ways to model your operations. In this case, we don't really want. There are a number of reasons we don't want to do that. It gives us less ability to characterize exactly what is serializable. It requires, in some cases, reliance on undocumented behavior. You'll see this in almost every library that's doing anything complex with runtime reflection in this domain. And that's going to also be the case for the implementations that we're looking at, but they will fail at compile time, not at runtime, or they're more likely to fail at compile time. And there are some advanced features that we probably won't have much time to talk about today in Circe's implementation, like what I'm calling partial decoders or patching decoders that rely on the fact that we're doing all this stuff with types at compile time. Okay, so just to summarize, generic derivation, it's something that at compile time allows us to take our ADTs, our case classes, map them to a generic representation, and then create type class instances for what the type classes that we're working with for those representations. All right, and then this is one of the things that sets generic derivation in Circe apart from libraries like scodec. So when I started working on the fork, I had a few principles. One of them, I wanted to keep the core module with as few dependencies as possible. And then I also wanted, and these go hand in hand, I wanted the generic derivation to be something that users opted into. So you wouldn't just get generic instances thrown at you if you didn't want to have those instances. This is something that you intentionally had to bring into your code base. And then also that there could be competing implementations of generic derivation. So I would provide one in the Circe repository, but users could provide their own. They could build their own, publish them, and other people could use them. So that means that, we don't have access to these shapeless representations in Circe core. It also means that we can't actually put this instance derivation in the companion objects. And that's going to cause us a lot of pain over the rest of the talk. That if we could put those instances there, it would mean that this wouldn't be opt-in in the same way. We couldn't plug in other implementations, but it would make a lot of things a lot nicer. So we'll be talking about how we will work around that. Okay. So the first approach, which I'm going to skip over really quickly, would be let's not use these nice generic representations at all. Let's just write macros that inspect our types and then spit out our type class instances. And this is entirely possible. Everything we do today is only possible because of the macro implementation. But in this case, there are a few libraries that do provide some kind of instance derivation without using a generic representation like Shapeless provides. So Argonaut has a simple version of this. PlayJSON has the inception capabilities that allow you to derive instances for case classes. And there's an extension of that called PlayJSON sealed that gives you something similar for ADTs. All these just use macros directly. This has some nice things about it. It doesn't bring in extra dependencies. The compile times, as we'll see in just a bit, are relatively fast compared to the more featureful, more complex, or more elegant shapeless implementations that we'll be looking at. But it does complicate the maintenance story in a number of ways. So macros, they are experimental. There are changes between Scala 2.10 and 2.11, to a lesser degree between 2.11 and 2.12, but then as we move over to future versions of Scala, it is likely to get increasingly more complex. So not bringing macros into our own implementation, but simply using these nice operations that Shapeless provides, like the generic machinery, like lazy, which we'll talk about, makes the maintenance story a lot easier. Okay. So no, we're not going to go with that approach. So this is the. So we've said, okay, we want Shapeless here. We want to be able to let Miles be the one who worries about keeping our macros up to date and working on future versions of Scala. That's not something that we want to do ourselves. So this is a big block of code, and it can look intimidating, but this is a working implementation of if you have a Circe core dependency and a Shapeless dependency, you can paste this code into the REPL, and you have generic derivation for case classes for decoder instances. This will just spit out your type class instances for any case class that you throw at it if the case class has instances for all of its members. And talk just briefly about how that works. So what we're doing here is we're inductively telling the compiler how to build up these instances for our H list. So we say if we're at an empty H list, then we just ignore the input, ignore the JSON value, and just return an empty H list. If we're trying to get an instance for one of these labeled values in our H list, where the K here just represents the member name at the type level, and then the H represents the member type, this will give us an instance for that piece of the H list appended to the tail. So this is just it's a fairly straightforward inductive description of how to build up instances for H lists. And then the last part here is the part that tells us how to map between those H lists and our case classes. So Shapeless is providing two things. It's providing the machinery that we need to, it's providing this generic representation, the H list, and then it's providing this mapping between H lists and our case classes. Okay. So skip through. Now we know how to decode H lists. We have this mapping from a type like this, our case class that we had before, to this H list where each of the members is annotated with a type level string. This isn't exactly the syntax here will only work if you have the literal syntax in the new type level Scala. Okay. So this works for many simple examples. We can expand it. We can do the same thing for encoder, and it looks almost exactly the same. So that's nice. And then we can also do the same thing for ADTs. So we've just done this for case classes. We can also do it for our sealed trait hierarchies. And all four of these instances, these kinds of instances, look very similar. And in the repository, you can see these examples. Okay, so there's this kind of, this is, because this isn't the direction that Circe went or that most of these libraries went, I want to skip over this really quickly, but it's a really nice idea. Because all these implementations look really similar, and implementations for kinds of type classes that don't have anything to do with serialization. So if you look at generic derivers for equality type classes or show or arbitrary, all of these type classes, the instances will look almost the same. You're telling the compiler what to do on the empty cases and then on the inductive cases. And so there was this idea, like, these are all type classes. We want to be able to characterize these types that don't have any other relationships, so we're going to define a type class. And this is actually available in Shapeless. We can write an instance of our type class for our encoder type class, And I've left out the implementations here because they're almost identical to the ones that we just looked at. But that's all we have to do for that part. And then this is only a couple thousand characters. This is a tiny, tiny little piece of code, and it gives us encoders, decoders for case classes and ADTs. So we've really accomplished a lot with this type class. It gives us a very concise way to define our type class instances or derivers. Okay, but it has a lot of problems, or it has a number of problems. So one is the type class really expects you to have this built into your companion object for your type class. So this would have to be something that we could actually build into our encoder companion object for it to work naturally. And that's something that we've said that we don't want to do for Circe. Another issue, which we'll talk about in more detail in just a minute, is this issue of prioritization. So the instances that this type class, or that this implementation of generic derivation gives us, will override explicitly defined instances, and that's not what we want. And then let's see. So yeah, the definition order, that's something that we'll mention really briefly, and then there are other cases where it's just unclear why it doesn't work. So yeah, before I made this, I cheated a little bit here by importing only from the encoders package, and then doing my encoding, then importing from the decoders package, doing my decoding. And if I import them together, nothing works. I've got collisions because of the way that the type class is implemented. So it's a really nice idea, but if you can't bake it into your companion object for your type class, it's not as useful as you'd like. So we're going to leave that aside. That it would be beautiful if it worked. It's not going to work for us. Okay, so our more straightforward approach, we fall back to where we were just before. It's pretty great. It has a few limitations. So it doesn't work for recursive data types. We still have to worry about prioritization. And it still has these other issues with sometimes you have to move around your code to get it to pick up the instances. All right, so here's a very simple version of where it breaks down on a recursive data type. So we've got this simple representation of a list of integers. We want to derive a decoder for it, but it will say, no, I cannot do that. The compiler is going to diverge while it's looking for those instances. But if we had something simpler that wasn't recursive, like a representation of options that aren't generic, that just hold an integer or not, it would work just fine. So this is actually an easy case. This is the easiest of these problems that we'll look at all day. We just stick this lazy this lazy wrapper that Shapeless provides around our type class instance, and we're fine. We're set. We have to do that, I think, in this case specifically in 2 places in our code, and now we get instances for these recursive data types. So that's a nice simple problem. We were able to solve it with this little piece of machinery that Shapeless provides. But the issue of priorities is a lot more complicated. So here we're taking this list of integers and we want to encode it as JSON. So I'm using this simple package here as the Shapeless implementation that we were just looking at. It's available in the repository if you want to look at it in more detail afterwards. But when we import the contents of that package, if we try to encode our list of integers now, we're going to get this bizarre representation of the list of integers, not at all the one that we want. And the problem here is that the way that implicit resolution works in Scala is that it's going to look in a couple of places. So it's going to look at identifiers that are available in the current scope. So these could be defined. They could be defined in some kind of enclosing context, or they could have been imported. And then it's also going to look in the companion objects for the types that are associated with the target type. And it will always choose an explicitly imported instance over a companion object instance. But in this case, because we can't put encode generic, this method that provides us with our instances for case classes, in our encoder companion object, we have to import it. But it provides instances for case classes. The list in the standard library is a case class, so that instance for case classes is always going to win. So that's why we get, this is the representation that we would get if we didn't have any instance for list defined in Circe, and we just applied the generic derivation, which is basically never what we want. Okay. So there are a few ways to handle this. So this is generally a problem with instances that are orphaned, that are not defined in the companion object of either the type class or the type that you're characterizing. So there are a few ways that you can approach this. This one I'll skip over really quickly because it doesn't really fit the way that Circe is built. So in SprayJSON Shapeless, which is it's Sam's project that in the Shapeless for Mortals that I mentioned, that's a kind of lead up to the implementation there. It works well for SprayJSON because of the way that SprayJSON provides its instances, but it's not going to work for Circe. So I'll skip over that. This one's a little bit more interesting. So Shapeless has this really strange. So if I had to vote for what I thought was the spookiest thing in Shapeless, it would probably be this low priority thing that you put it in your implicit your list of implicit parameters, and it will fail that derivation if there already exists an encoder in scope. So this is really scary magic to me. That it works great here. It's a nice, in some way arguably nice, general purpose solution to this problem. But it makes me uncomfortable. I don't want to have these pieces of magical implicit evidence on all of my generic derivation methods. So this, again, it's just a matter of personal taste that I think Argonaut Shapeless is a great library. This just isn't the route that I would choose to go here. Okay. So the solution that Circe uses is inspired by, and it originally was, explicitly export hook, which is another one of Miles's libraries. So what this allows you to do is you have your companion object for your type class extends a low priority trait that has this importer. So this importer looks for instances of that type class that are in this export wrapper. And what this allows you to do is basically your generic derivation provider can sneak instances into a lower priority in this prioritization. So they in a sense look like they're coming from this low priority decoders trait, which will be, everything there will be a lower priority than the contents of our decoder companion object, or than things out that we've defined or imported out in the world. So we can kind of sneak these instances into a very low priority where they'll only be picked up if nothing else is available. Okay. Okay, so that's another problem. It was a little bit harder than the recursive data type problem, but we solved it. I think that this is a good long-term solution. So now that gets us basically up to where Circe was at the 0.3 release. And it works great. You can check out the better package in the example repository to see this implementation, to see how it works. The issue is that we've added all this stuff onto our nice, simple, shapeless implementation, and we've made compilation really much slower than we'd like. So if we actually grab Circe at this point, we have a repository with the Circe generic dependency for the 0.3.0 release. We look at the quick start in the README, and we paste that code into the REPL. I won't do it now because we don't have a lot of time, but we paste all our definitions, we paste our foo instance, and then we derive an encoder for foo with the second to last line. On my laptop, that will take 5 or 6 seconds. And it's all compilation, it's not runtime. And then the next line will take even longer, it's 6 or 7 seconds. And that's embarrassing, that it shouldn't take that long to compile to derive these instances and compile them. Okay. Yeah, and this is entirely a runtime issue. That we've got benchmarks in Cersei that show that, there's a tiny bit of overhead involved in the generic derivation, but it's not enough to worry about in the vast majority of cases. It's going to be on the order of a few percent. That if you're concerned about performance, it's going to be compile time performance, not runtime performance. Okay. So there are two ways that Cersei has been working to make this experience less horrible for users. So the first one is we want to avoid requiring things to be derived over and over. And this has a side effect of making Cersei feel a little bit less magical. And we'll look at that in just a second. The other version which we'll look at after that is attempts to make the process of derivation actually faster. Okay, so this code here, this is going to derive the foo instance. So when we call as JSON, that requires implicit evidence in the form of an encoder foo argument. And so that will go off to the derivation mechanism, have it create an instance, and get it back. And that will happen for every one of these lines. So we're not really, Cersei's not providing a way to have those instances cached automatically. Yeah, so that could be done only once. In this case, it's being done 3 times. That's also the case if we have the same type that needs a generically derived instance multiple times in a case class. So this will also look up or derive instances 3 times for foo. Okay. So the semi-auto mechanism is a way to make this. You still get most of the advantages of generic derivation. You avoid a lot of boilerplate, and you get something that it's more explicit. It's less magical. So this allows you have your instance in your companion object for your own type, your own case class or serial trait hierarchy. Or you have it in some kind of protocol object. You can use any pattern you're comfortable with for defining your implicits, your type class instances. But you do have this one line that goes to the generic derivation mechanism and says, build me an instance for this type. So it's one line of boilerplate, but you don't have to tell it anything about the type. And then that will just be derived once, cached. And the other nice thing is that you don't get instances for everything. You only get instances that you ask for. So at this point, I think many to most of the people who I've talked to who have adopted the library are using, at least for a large subset of their types, the semi-automatic derivation as opposed to the automatic. And it can have a huge impact on compile times. So that's the easy way, or the easier way. It puts more of the burden on the user of maintaining that little bit of boilerplate. The harder way is something that I introduced in Cersei 04. So here, if we remember how the actual derivation process works, so we take our case class, we get our generic representation, and then we've described how to build up instances inductively for those H-list or coproducts. And then the implicit search mechanism has to basically go in reverse to find instances. So if we've got a really, really simple case class like this, what's going to happen is when we ask for a decoder instance for that type, it's going to find our decode generic. That's going to trigger a lookup for an instance for our H-list representation, which is going to get the cons decoder, and then we'll have 2 searches for an int instance and an HNIL instance, and then we'll get those, and then we'll build up our instance for our case class. So this is using a very general purpose mechanism in the implicit search system that's not really tailored to these generic representations specifically. So the trick that we use is so we use shapeless to give us our generic instances. So the 2 sides of this, that shapeless is providing our representations, it's providing our generic instances, and then we're telling how to build the instances for our case class and our ADTs. So shapeless is it's still giving us the representation, it's still giving us the mapping between our types in that representation, But instead of then using this kind of inductive definition of how to build up instances, we're actually going to just take that HList, and then in a macro, we're going to just fold over it directly. And that allows us to avoid repeating searches if the same type shows up more than once. It lets us perform a lot of little implementations. And this is something that the Miles and the type level Scala group have promised is a priority for work on the type level Scala compiler that should eventually make its way, or possibly make its way back into the Scala compiler. That this would be more generalized improvements to the implicit search system that would allow it to see these patterns. It can see, hey, it looks like I'm doing this kind of inductively building up instances for something like an HList and optimize them in this way. So in Cersei, it's not generic, or it's not generalized. It's just specifically implemented this way for our encoder and decoder. Okay, so when I was developing this, I don't really want to admit this, but my benchmarking was pretty ad hoc. That I was watching how long my test suite compile times took. I was publishing snapshots and milestones and talking to users about how it impacted their compile times, but I didn't really have any kind of, I just hadn't taken the time to benchmark it in any more formal or rigorous way. So it works, but just over the past month as I've been preparing the example repository here, I've noticed a number of things that can be improved still. So this is what it looks like for, so I'm deriving case classes. The x-axis here is the size of the case class, the number of members. There are 5 different types, and they're repeated however many times. And this is the compile time. This is still pretty simplistic. I'm just using Shapeless's new compile time macro. But it seems to match it seems to match the numbers that we got from our more informal performance evaluations before. So it's about half the compile time for the Cersei generic 05 compared to our. So the correct shapeless version here is it's our more or less feature complete shapeless 03 version. No custom macros, just shapeless, but it has all the same features as the current Cersei generic. And then down here we have our naive version, which has all these things it can't do, but it's relatively fast. And then at the very bottom we have the raw macro version, which can't do a lot of things. It can't even handle generic case classes, but it is really, really comparatively very fast. Okay. How am I doing on time? Okay, I'll go pretty quickly through this. One thing that this is also this makes me wish that I had done this kind of this simplistic benchmarking a lot earlier. So that's what it looks like here. This looks great. This is up to 10 case class members. That's what it looks like when we go up to 30 case class members. So this is horrible. I'm embarrassed that I released a library with this, but most people don't need case classes with 20 members, I hope. But yeah, so the red line here is the current behavior in Cersei 051 of the generic derivation, and that's due to it's a case where I have a white box macro that I think is being constrained by the constraint on a subtype constraint on the type parameter. And because it's a white box macro, that's not having an effect. So I have to immediately crash the derivation if my type doesn't actually conform to the type that I expect. So it's a very easy fix, but it's something that's set in Cersei for an entire minor release cycle, because we didn't have this this ability to do this benchmarking. So I've got a fix for it. It's just a few lines. And now we have something that looks even better. So this is deriving up to case classes with up to 30 members for first our previous CERC generic version, then for our new optimized version that does this looking for collapsing the inductive search down to just a folding over the case class members. And that patterns pretty closely with the naive, incomplete, shapeless version that we started out with. There's not a lot of overhead, even though it's handling a lot more of the difficult parts and corner cases. Okay. And then these are the same numbers for, instead of now widening the case class, deepening it, where we have nested case classes up to 30 levels deep. We get actually more improvement there than in the widening version. And then it's pretty similar for ADTs. So this is broadening the ADT. We have a seal trait with a bunch of case classes that inherit from it. And here again, we have the same basic ordering. The correct shapeless version is relatively slow. This optimized version patterns much more closely with the naive shapeless version. Okay. This still isn't good enough. That's still not great that it's taking, if you have 30 pieces or case classes in your ADT, it can take up to 2 seconds to derive a decoder instance for it. So that's not great, but it's a lot better than it was before. Okay, and that's something that we're working on. Now, the last thing that I want to talk about is, so these are since people have actually started using CERC over the last 8 or 9 months, these are by far the most requested features. So everybody wants to use generic derivation, but then they realize that they don't want to name their case class member, use snake case for their case class member names. But they need snake case on the JSON side. Or Shapeless has one way of modeling sealed traits, and that's not what they want. They want a type field instead of this object wrapper that CERC uses by default. Or they want a different way of representing case objects, or they want to use default values. CERC doesn't do any of these things off the shelf. You have to define your own instances if you want these things right now. So I put together a really early implementation of this last January, and that's been sitting in a pull request in CERC since January. I've been working on it. It's been on the back burner. Every once in a while I'll try something new out, or I'll make it a little more consistent and clean. But I've been promising to people this feature for months now. But there are a few ways you can do this. So the Spray JSON Shapeless project that I mentioned earlier actually allows you to, it gives you some fairly nice ways of configuring your generic derivation. So it has these hinting type classes that allow you to, you put an instance of the hinting type class in scope for your type, in addition to then the type class instance that's derived for it, and the derivation will use those hints to guide the derivation process. Another approach would be to just make our derivers configurable, so that we build up a deriver and then we import its contents, and it provides derivation that has the features we need. And then the last way would be to make everything type-driven, and I'll talk about what that means in just a second. So I think I'm pretty low on time, so I'll skip over this. I'd encourage you to take a look at the generic derivation configurability in Spray JSON Shapeless. It's not an approach that I want to use in CERC, or I want to try to use a more explicit or specifically type-driven approach. But there may be a few cases where I fall back to this approach. But I think it's a really nice implementation of this idea. Okay. The configurable drivers, I've experimented with this, where I do just have the user defines a driver, imports its contents in the same way that they would import the contents of CERC generic.auto. It works, but it's not as flexible as we want, and I don't think that it's going to be a viable solution in the long term. And then just a quick preview of the solution that will be in CERC. So we have an extra configuration type parameter on our encoder and decoder type classes. And then a driver can look at that type parameter and use it to configure the derived or the instance that it derives. And so users, when they put a type class constraint on their method, asking for an encoder or decoder, they can request configuration there. There are also some helper methods that we'll see in just a second that allow you to specify configuration. Or you can just use the semi-automatic approach and say, when you're asking for an instance from semi-auto, you can give it the configuration parameter. And this works like this. So we import the contents of Circe package, our decode method from the John package, our as JSON syntax, and then our standard generic auto, and then also this generic config thing, which will give us our configuration types. And now we can say, OK, we'll create a foo. Instead of as JSON, we're going to say as JSON configured and say we want this encoded as snake case. And we'll get then a JSON representation that uses snake case. And we can do the same thing with, on the decoding side, we can use this decode configured helper method. And so we can read back that JSON string that we just wrote into a foo type. And then we can also, since we have a default value for this case class, we can try to decode an empty object, and it will work just fine if we specify this use default values configuration parameter. And we can compose these configuration types together to use more than one at once. These are basically phantom types. Behind the scenes, at the implementation level, they do work, and they are instantiated, but that's just implementation level. It's not user-facing. There are a lot of complications here around whether you want, if you ask for a configured map of strings to list of users, for example, whether you want the configuration to go all the way down. For the implementation that I'll be releasing, that is the case, and then, but that introduces complications. So things like this are especially tricky, where I have a configurable type foo here inside of a generic type list, which has a non-configured instance or a default configured instance, and then that's inside another configurable type. In this case, I found it difficult to make the configuration reach through the list down to the inner foo, but I have what I think is pretty close to a working version of that. OK, so configurability is coming soon. There are some other things that I'll be working on, like caching for the auto instances, so that even if you want the kind of magical auto experience, you can still get the caching that you would get from semi-auto. And then there are lots of things. So in the type-level Scala compiler now, there's a fix for most of the problems that come from this SI 7046 issue, which this is the one that can make a mess of things when you try to request an instance in the same scope that you've defined your case class or sealed trait hierarchy. So that's something that I've had to warn people about when they work with Circe generic. That's something that people run into and then complain about. And if I haven't warned them, and that's something that hopefully soon will be a non-issue. OK, so that's let's see. Does somebody have? I lost track of time. How much time do I have left? 5 minutes? OK. So since we've got a couple of minutes left, I'll just do a quick. So I mentioned earlier that there are some nice things that that doing this at compile time at the type level gives us. This is one of the features of Circe that I think really shows off the possibilities for generic derivation. So this is something that we've had since Circe 02, which I think came out last September, maybe October. But this is a very, very common use case if you're doing any kind of web development or building JSON web services, that you'll have a case class, but you don't want to exactly, this is your representation in your data model of your, in this case, user. But you don't want to decode literally every single one of those members. that the JSON that you're actually getting is that case class, but it's missing something. So say that a user is posting a new, some client is posting a new user to your service. You want to pick the ID for that user. You don't want that to be included in the incoming JSON. So the solution that you see in many cases where people are doing this in Scala is to provide this kind of extra case class that's almost the same shape but doesn't have that piece. And then they can use generic derivation, or they can use some other method to parse that JSON into that partial type. Sorry? OK. So what Cersei provides is this way of, instead of defining an extra case class, we can actually decode the incoming JSON into a function from whatever the missing piece is to user. And this is all done through shapeless. There are no new macros here, no fancy tricks. This is just shapeless, the different kinds of implicit evidence about our types that we can get from shapeless working together. So here we've got our incoming posted JSON. We've got our user type that contains that contains an extra ID member. We can decode that incoming JSON into a function from long to user, and then we can provide the ID that makes that a complete user. So that's something that we can only do in this context because we have these really nice representations and these really nice ways to characterize those representations. OK, so thank you. I guess we'll have a couple of minutes for questions, or? Sorry.
No time for questions, I'm afraid, as we've been running quite far behind. So we're going to go straight to lunch. But do feel free to come down and ask some questions in person.
Thank you.